Bronsted Lowry acids and bases. Bronsted and Lowry defined acids as proton donors and bases as proton acceptors. And again, H plus is just a symbol for a proton, right? It's a hydrogen atom without the electron. Before the donation, the acid consists of an H atom bonded to a conjugate base. A conjugate base is the base formed after the donation. A base is a proton acceptor. A conjugate acid is the acid formed after the base accepts a hydrogen atom. We'll use the symbol capital A to represent a conjugate base. So the general formula for an acid is HA, in which H represents a hydrogen atom and A represents a conjugate base. HA will then separate into an H plus cation and an A minus anion. On the left side of this equation, HA is the acid and water is the base. Observe that HA donates its hydrogen ion over here to water on the left side to form hydronium, and A minus on the right side. The transfer of protons is circled in red. Over here to there, and over here to here. Note also that the H plus ion, again otherwise known as a proton, transfers positive charge with it, so that the hydronium ion has a positive charge and A minus has a negative charge. But this equation can proceed in either direction. Let's see how the definitions work going from right to left. Proceeding from the right side, the hydronium ion will donate a proton to A minus. So on the right side, this is the acid, it's the H plus or proton donor. This is the base, it's the proton acceptor. In this case, water is the conjugate base since it is the base formed after hydronium made the donation. HA is the conjugate acid since it's the acid that forms after A minus accepted the donation. Another example, ammonia plus water gives you the ammonium ion plus the hydroxide ion. So when an ammonia molecule accepts a proton from a water molecule, it is acting as a base, and there is a resulting increase in hydroxide concentration. The Bronsted Lowry definition of a base is less limiting since it properly classifies ammonia as a base. In this case, water is serving as a proton donor, making it the acid. An important property of water, we're going to put a box around this one, is that it is amphoteric. It can be a base or an acid depending on the other reactants. Once again, acids are defined as proton donors. So here you have hydrogen fluoride acting as a proton donor, so what? It is an acid. Bases are defined as proton acceptors. For example, here the cyanide anion is acting as a proton acceptor, right? It turns into HCN over here. Let's work an example. 1. Identify the acid and base on the left side, then identify the corresponding conjugate acid and base on the right side. The acid on the left side is hydrogen fluoride since it will donate an H plus ion or a proton. And what happens is it then turns into fluorine ion because it gave up the H. The base is water since it will accept an H plus ion, turning into hydronium. The conjugate base to hydrogen fluoride is F minus fluorine since that remains after hydrogen fluoride donates the H plus ion. The conjugate acid to H2O is H3O, the hydronium ion, since that results from water accepting the H plus ion or proton. A Bronsted Lowry acid must contain a hydrogen atom. Acids are abbreviated as HA. The H signifies a hydrogen atom, which will form the H plus cation, and the A signifies the anion, which will form. So we have hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and sulfuric acid. Acids have different numbers of acidic protons. A monoprotic acid contains one acidic proton, hydrochloric acid there, 1H. A diprotic acid contains two acidic protons, sulfuric acid, see the little 2 there? A triprotic acid contains 3 acidic protons, right there, phosphoric acid. Diprotic and triprotic acids are 2 types of polyprotic acids, acids that can donate more than one proton or H plus ion. A Bronsted Lowry acid can be neutral or it can carry a net positive or net negative charge. Here's neutral. Here's a net positive charge. Here's a net negative charge. All three are Bronsted Lowry acids. Let's move to bases now. A Bronsted Lowry base is a proton acceptor, and so must be able to form a bond with the proton, which is represented by H+. The base must have a lone pair of electrons, B with kind of a colon mark there where B is the name of the element, that can be used to form a new bond to the proton. The nitrogen atom of ammonia, NH3, has a lone pair. Right here, see the N colon? Water acts like an acid this time and donates its proton to become OH-. Ammonia acts as a base and accepts the proton from water to become ammonium. Lone pairs make these compounds bases, which weren't bases in Arrhenius' scheme. The hydroxide group in metal salts make these compounds bases: sodium hydroxide, potassium hydroxide, magnesium hydroxide, and calcium hydroxide. Bases can accept different numbers of protons. A monoprotic base can accept one proton and release one hydroxide ion to an aqueous solution, e.g. group 1 metal hydroxides. A diprotic base can accept two protons and add two hydroxide ions to an aqueous solution, such as those formed by group 2 metal hydroxides. Which of the reactants in this reaction act as an acid? Which acted as a base? HSO4 donated an H+ to become SO4. Right here, see how it lost the H? So therefore, HSO4 acted as an acid. Cn- accepted an H+ to become HCN, right? No H here, and here it has the H. Therefore, Cn acted as a base. Which of the reactants in the reaction acted as an acid? Which acted as a base? Methyl ammonium, it's this guy over here, donated an H+ to become methylamine. See how this has two hydrogens? This just has the three. Therefore, it is an acid. Water accepted an H+ to become hydronium ion. Over here, see it picked up, that's three H's, here there's two. So that is a base. Water is acting as a base this time. Some acid-base reactions are reversible, so we can also identify acids and bases for the products. For example, we have fluorine plus water yields hydrogen fluoride plus hydroxide. Hydrogen fluoride donates an H+ ion to become fluorine. Therefore, it is an acid. Going this way here. Hydroxide ion accepts a proton or a hydrogen ion to become water. Therefore, it is a base. So we have base, acid.